All right, so today I'm taking attendance, so please put your name and email address on this sheet. Also, let me know how you're doing. I care, right? I care. Those of you that are engineers and not emotional, you can give your answer on a scale of 1 to 5. That was a joke, right? Okay, so things that we're looking forward to. There's an optional ACS standardized exam. I really encourage everybody to take it. You know, there's nothing that you can lose by taking it, and there's a lot to gain. Plus, it can reduce stress during finals week. All right. Now, I know for our exams that we've had on Tuesday evenings, I've had some students that aren't able to take the exam with the rest of the class because they have class conflicts. Is there anyone that has a class conflict on Thursday of Dead Week? Right. If you do, you need to contact me soon so that we can arrange an alternative time. All right. I'll be announcing, well, actually, your final exam, if you're registered for this class, will be in this room. All right. And then I'll be sending out an email asking for folks to get in touch with me if there's some need to alter the exam time. Okay, any questions about exams? The other thing that we'll be announcing soon, and I don't have the rooms yet, will be the review sessions for the final. Okay? All right, so moving forward, we've been talking about Maxwell relations. Maxwell relations, we've pointed out, are cross derivatives, right? And those are equal to each other because they are referencing an exact differential. So we've shown that they're pretty important and that they allow us to get relationships between things that are measurable in the laboratory or things that can be easily determined from equations of state and relate those to quantities that aren't so much easily measurable or calculable. We've also reviewed natural variables. And then the last time we met, we've been exploring the differential of the Helmholtz and Gibbs energies. So specific things that we've gotten out of that is we've seen the entropy dependence on volume and pressure, and we've looked at some examples. We saw that we could calculate delta S for isothermal expansion of an ideal gas pretty straightforwardly. We also pointed out that this is a good way to calculate deviations in entropy from ideal using a large volume or a low pressure as one of your limits. We've also looked at the dependence of the energy of the system on volume and the enthalpy dependence on pressure. The homework that's due next Friday will have a couple applications of that. And then we talked about the Gibbs dependence on pressure, Gibbs energy. All right, so, starting with our differential that we derived last time, we saw dg dt is equal to minus s. That tells us that if we plot the Gibbs energy as a function of temperature, that's going to get us the negative of the slope. And we're going to apply this today and in the next chapter. Right? And then dg dp, plot of g versus pressure, that's going to give us a slope equal to the volume. Okay? All right, we've looked at differential equations for the total energy of the system, enthalpy, the Helmholtz energy, the Gibbs energy. We've determined their natural variables, and we've looked at their Maxwell relations. Right? I also mentioned last time, and I'm going to reiterate this, we've been tossing a lot of letters around. Make sure that you connect those letters with thermodynamic concepts. It can get confusing. Okay? All right, and then where we ended last time, at least I think this is where we ended last time, dg dp for the molar Gibbs energy is equal to the molar volume. Now we can rearrange that and say at constant temperature, the change in the Gibbs energy is equal to the molar volume times dp. This is absolutely general. And then if we say, let's assume we have an ideal gas, then we can say that the difference between the Gibbs energy at one pressure and another is given by RT ln P1 or P2 over P1, right? And we'll see that this is pretty important. We're going to be using this down the road, all right, and some related equations. All right, so we're also going to talk about the Gibbs energy dependence on temperature and how we determine the Gibbs energy at any temperature for an ideal gas. That's going to be a derivation of Gibbs-Helmholtz equation. We'll talk about determination of Gibbs for a non-ideal gas, all right? And so that means we're going to be basically extending that equation to a non-ideal gas situation. That's going to lead to an introduction of fugacity. How many people have heard of fugacity before? A few of you? Okay. All right. So we'll be talking about fugacity. We're going to be relating Gibbs energy to phases and phase transitions, and then we're going to introduce chemical potential. Okay. All right. So the last time we met, I made a mistake. So let's correct that first. So the change in the Gibbs energy is going to be the integral between P1 and P2 of, this should just be RT over P. And that's because I'm using a molar Gibbs energy, all right? So we've already accounted for the number of moles. We've said there's 1, okay? All right, so if we choose to let P1 be 1 bar, then what we can say is that delta G is equal to the molar Gibbs energy at some temperature and pressure minus the Gibbs energy at some temperature. Whoa, we're starting off rough. Temperature. And then I have this little degree symbol, and we know that that degree symbol references 1 bar. All right, and that in turn is RT ln of P over 1 bar. Okay, all right, and then what I can do is a simple rearrangement of this equation. All right, and this basically says that the Gibbs energy at any pressure and temperature is going to be given by the Gibbs energy at 1 bar at that same temperature plus RT ln P2 over P1. So this is an easy way to get the Gibbs energy at a pressure other than 1 bar, right? So this equation is important, and we're going to be building on that, right? And if you think about where this equation came from, we needed to assume that we had an ideal gas. So this doesn't work for non-ideal gases, okay? All right, so next up we want to look at the Gibbs dependence on temperature, all right? So this is a little bit more complicated of a derivation. It's pretty straightforward, but what we do is we start with the definition of the Gibbs energy. We divide both sides by T, and then we take the derivative of that with respect to T, all right? So I've done that with the first term, the derivative of G over T with respect to T. Next up, I need to take the derivative of H over T. All right. Well, that's going to be a product of the enthalpy times 1 over T. All right. So the derivative of this is going to be the derivative of H with respect to T times 1 over T, and then the derivative of 1 over T with respect to T times H. Okay. All right. So I'll just put that out there. That's going to be H derivative of 1 over T with respect to T, holding pressure constant. And then next it will be 1 over T, the derivative of H with respect to T, holding P constant. All right? Does anybody recognize what that is the same as? Let me ask this question. What's du dt? It's not CV. Du dt is CV. dH dt is Cp. All right? And so that really says this second term is Cp over T. All right? Now that's going to become important because you may recall that we've previously shown that ds dt is the same as Cp over T. All right? So when I come to this last term, I'm going to be subtracting minus ds dt at constant pressure. All right? And because this and this are equal to each other, this and this are equal but opposite sign, so I'm left with the derivative of t to the minus 1 with respect to t times h. Okay? All right, and what's the derivative of 1 over t? It's going to be minus 1 over t squared. So that means that we can say that the derivative of g over t is minus h over t squared. Okay? All right, because we're often interested in differences, we can say, well, if I'm interested in the difference between one Gibbs energy and another Gibbs energy at a temperature, I can do the same thing with the enthalpy. So this will be minus H2 minus H1 over T, or minus delta H, whoops, and I forgot a squared there, over T squared. All right? So this is what's called the Gibbs-Helmholtz equation, and it gets us the relationship between delta G's at different temperatures. So it gives us the temperature dependence of delta G. Okay? All right, so we can take this equation and rearrange it. It's still the Gibbs-Helmholtz equation, but this will be minus delta H over T squared times dt. Okay? And so if I'm interested in determining the difference between the Gibbs energy change at one temperature and another temperature, that means I need to integrate that, right? So that's what I'm doing here. So this is going to be the integral of d delta G over T between T1 and T2. And then I have the right side of this that I need to deal with, okay? All right, so we'll come back to the left side in a moment. But we know that enthalpy change does change with temperature. But in most cases, it's not a huge change, and if our temperature range is small, we can consider it a constant and pull it out front. All right? So that becomes minus delta H times the integral T1, T2 of dt over T squared. All right? Okay, so the next thing that we need to do is ask the question, what's the integral of dt over T squared? Right? Anybody remember what that is? It's going to be minus, right? But it's t to the minus 2 that I'm integrating. And so it's going to be t to the minus 1 as a result, right? So it becomes minus 1 over t, and then I'm going to put plus a constant. Right? Does that make sense? Okay, so that says that the integral here is going to be 1 over t between T2 and T1, all right? And the other thing that we notice here is I've got a negative sign, and I have a negative sign here. So that means I'm going to be able to make that positive overall, all right? So that means that we can say is going to be plus delta H, now 1 over T2 minus 1 over T1, and that's going to give me delta G at T2 minus delta G at T1. Okay? All right? And so my recollection, I haven't taught 178 for a while, but last time I taught 178, we did introduce this equation. It allows us to calculate delta G at any temperature as long as I know delta G at another temperature and I know the enthalpy change of the reaction. Okay? All right. So this is another Gibbs-Helmholtz expression, just in the integrated form. Okay, so the thing that we can do is we can say, well, we know that we can calculate delta G. And we know that there's a number of ways for us to do that, right? One way that we can do it is we can go to thermochemical data. I can go to enthalpies of formation, calculate delta H of a reaction. I can go to standard molar entropies, calculate delta S of the reaction. That gets me delta G at a particular temperature. We also can go back to basics and do an experiment. And so we can take our crystal down to 0 degrees, integrate from 0 up to the melting point over the heat capacity, and then add in the enthalpy changes for the fusion. So that's accessible to get us to delta H. And then, we've talked about how we can determine entropy. So we cool down to 0. Hopefully we have a perfect crystal, which means that S at 0 is going to give us a 0 value. And then from there, we're integrating the heat capacity over the temperature from 0 up to the melting point, and then we use delta H over T for each of the phase transitions. So at any rate, we have ways of getting delta H and delta S. Okay? Does that make sense? All right, so the next thing that I want to do is talk about a plot of the Gibbs energy as a function of temperature, okay? All right, so what we want to do is come up with an equation that we will, give us an ability to predict what we expect to see, all right? So we can take our Gibbs energy at some arbitrary temperature, reference it to 0 Kelvin, okay? All right? And then from the definition of entropy, right, so let me just write this down. Delta G equals delta H minus T delta S, okay? All right, so I'm going to write that down, and that in turn is going to be given by H at the temperature we're interested in relative to H at 0, right? That's our delta H, all right? And then I have my T delta S term, all right? So this is minus T S of T, all right? And because we're talking about delta S reference to 0 degrees, let me just write that down. S at 0 K we expect to be equal to 0, but because we're at 0, this is 0, right? All right, so that last term, minus T S of 0, all goes to 0, okay? All right, so there's only one other thing that I want to do to this, and that is I want to focus on G of 0. All right, so I'm going to change the pen color so that that's clear. So if I'm talking about the Gibbs energy at 0 Kelvin, that's going to be the enthalpy at 0 Kelvin, right, minus T times the entropy at 0 Kelvin. Right? And if we're at 0 Kelvin, that means this term goes away. So this becomes equal to H at 0 K. Does that make sense? Okay? All right, and so what we can say is that everything we've written is equal to G at some temperature minus H at 0. Okay? All right, so now we just step back and we look at the expression and we ask, what does this mean? What are we talking about here? All right? So we know that we can have absolute values of entropy. That's what the third law of thermodynamics tells us, right? What we also know is that we don't have absolute values of enthalpy or of Gibbs energy. There has to be a reference point, right? And so we're just referencing it to the 0 degree for enthalpy and Gibbs energy. Okay? Yeah.
The sign for the TS0, shouldn't that be a plus?
Oh, over here? Yeah. Yeah. But you're correct. Yep. Okay? Okay? All right, so the other thing we can realize is because these are just reference points and they're the same on both sides, I can rewrite the whole expression as the Gibbs energy at some temperature is given by the Helmholtz, or the enthalpy at some temperature minus T times the entropy at that temperature. Okay? All right, and these, whoa, that's really messy. Let me do something to clean that up a little bit. We'll just put that in a box so it's separate, okay? All right, so these and these are saying the same thing, right? The only difference is that in one case we're referencing the Gibbs energy and in the other case we're not, all right? But now, because I'm interested in a plot of G as a function of T, I'm going to go ahead and write what we expect, or try to write what we expect. There we go. All right, so on the x-axis, I have temperature. That means that this T is my x value, right? And I'm plotting the Gibbs energy. So that means that on this axis, I've got the Gibbs energy as a function of T. So that means that's Y, right? All right, so the next question is when x is equal to 0, that's whenever t is equal to 0, what's my function equal to? It's equal to the enthalpy, right? And so in essence, that's our intercept, right? And then I need to worry about the slope, right? And the slope, I'll just put the m in here. But if x is equal to T, the temperature, that tells me slope is equal to S of T with a negative sign in front of it. All right? And of course, we've already pointed that out. dg dt is minus S. Okay? All right, so the next thing that we're going to do is we're going to talk about different phases. If I'm at low temperatures, what phase are all substances going to be in? They're going to be the solid. And if I go to really high temperatures, they're all going to be gas phase. So intermediate, I've got the liquid phase. Okay? All right, so if we think about this equation, G equals H minus TS, the thing that we recognize is that those entropies for those different phases are different, right? So let me just write that down here. So I have S of the solid, S of the liquid, and S of the gas or the vapor. Okay? Now I'm talking about the same substance. Which one of these is going to be the largest value? The gas phase. And the minimum value is going to be associated with the solid. Okay? And so what that says is that my solid curve is going to have a different slope given by minus S of the solid than the liquid, than the vapor. And what we see is that these values are increasing, so I should see sharp changes in the slope. Okay? All right, so for the solid phase, I'm just going to draw on here an arbitrary curve. All right? So we know that that intercept corresponds to the enthalpy, and then the slope of this is going to be given by minus S of the solid. Okay? Make sense? All right? Okay, so it's pretty clear that what we can say is that as temperature's going up, this function, G, is going down, right? And that's because I have a negative slope. Okay? All right? Assumption underlying that, H is not changing all that much, but minus TS is going to be decreasing as I increase the temperature. Okay? All right, and then what we expect is that I also will have a different curve with a different slope that corresponds to the liquid phase. And I've drawn it steeper because we know that slope is greater because the entropy is greater. All right, so in this case, M equals minus S of the liquid phase. Okay? All right, so I want to talk about something that we're going to be covering in the future. But what we expect for any system, if there's going to be a change occurring, it's going to change in the direction to minimize the Gibbs energy, right? Delta G negative, that is delta G decreasing, is going to be the spontaneous direction. So this is basically telling us that in this temperature range, the solid Gibbs energy is lower than the Gibbs energy of the liquid phase, and therefore we exist in the solid. Once I get beyond this point, this temperature, then the Gibbs energy minimum corresponds to the liquid phase. Okay? But it's determined by the minimum Gibbs energy. Right? And then we'll put in that last phase transition. My linear functions are not looking so linear. And that will be a slope that's given by minus S of the gas or the vapor phase. Okay? All right, and then of course, what temperature is this occurring at? That's going to be our melting point or temperature of fusion. And this will correspond to T vaporization, or as we'll see, it's also the boiling point. Okay? Does that make sense? Yeah.
What happens with the
I'm not sure I'm getting what you're saying, but that continues. You know, you can draw that function all the way up there. It's just that we are worried about the one that's the lowest Gibbs energy. All right.
Those slides represent like super heat or super cool.
Yeah, I would say that they would. Yeah. Yeah, I would say that they would. Okay? All right, so the other thing that's true is that if we look at the phase transitions, what we have is a situation where the Gibbs energy of the two phases are equal to each other, right? The curves are crossing there. So we can say Gibbs energy for phase 1 equals the Gibbs energy of phase 2, and by extension, delta G of that phase transition is equal to 0, right? G phase 1 minus G phase 2 equals 0, right? Okay? And that occurs as long as we're at the temperature of the transition. Okay? All right, so this is all review. We've covered it before. We've seen that the Gibbs energy is a function of pressure and temperature. We can do a total differential. We also have shown that dG is given by VdP minus SdT. Putting these two equations together, this tells us that dG dt is the same as minus S, and dG dP is the same as the volume. Okay? And in the next chapter, we'll look at G as a function of P. Okay? We'll also review G as a function of T. Okay? All right, section 8. Bear with me for a second. Is where we introduce fugacity. And fugacity basically lets us use this equation for non-ideal gases. Okay? So it allows us to account for non-ideal behavior. Again, just a little reminder. We've derived this expression assuming an ideal gas. We see that this is pretty easy to calculate with. All right? So rather than coming up with a new equation for every different gas, I'm going to take this equation that works for ideal and extend it to non-ideal behavior. All right? So the way that we do that is we introduce something called fugacity. And it's defined through this equation. G, as a function of pressure and temperature, is going to be given by the Gibbs energy at 1 bar at the temperature that we're referencing, plus RT ln. Right? So up to this point, we see no difference between this equation and our new definition. So what we're going to do is we're just going to put fugacity in for pressure. All right? And that's going to be referenced to a reference point for fugacity. All right? Okay, well, it would make sense that F naught is going to be 1 bar. So we choose the same reference point. All right? And then what we can say is that, well, if this gas is behaving ideally, I expect F to be the same as the pressure. Right? Under what circumstances do we have ideal gas behavior? Low pressures. I don't know who said it, but that's correct. So as P approaches 0, then we expect F to approach P. Right? And if you just compare these two equations, you're going to say, oh, there has to be a relationship then between fugacity and the pressure. Right? And so what we define the fugacity through is the fugacity coefficient, and that's defined as F over P. And I can rearrange that and say the fugacity is equal to the fugacity coefficient times the pressure. Okay? Does that make sense? All right, so let's step back and ask the question. if my gas is behaving ideally, what's the value of the fugacity coefficient? It's going to be 1, right? So fugacity coefficient 1, pressure is the same as fugacity, I have ideal behavior. Okay? All right, so that's what we have down below. So I want to talk about that a little bit. So this is F over P, which is the same as the fugacity coefficient, right? And what we see is that in the limit of low pressures, it converges on 1, right? And that basically just reiterates that in the limit, as pressure approaches 0, I expect ideal behavior, right? So thinking back to chapter 2, when we saw deviations from ideal behavior, we saw one thing occurring in the mid-range of pressure, and then a different thing occurring or causing the observations at high pressure. What's responsible for the mid-range dip in this fugacity coefficient? It's going to be the changing compressibility factor. So what were you going to say? Intermolecular forces. And we have two kinds, right? We have attractive and we have repulsive. So this region that's low but not high pressure is going to be due to what kind of interactions? That's where we have attractive interactions dominating. And then at higher pressures, this is where we have repulsive. Okay? All right, and I feel really bad writing this next equation here because we just don't have time to derive it. But somebody alluded to it. So we would expect that this deviation is somehow going to be related to the compressibility factor. And in fact, it is. It turns out that the natural log of the fugacity coefficient is given by the integral from 0 to some pressure, right, of z minus 1. So this just remind everybody, z is p v bar over RT divided by p and then integrated over pressures, right? So I want to just mention something about the math here real quickly. When I use P as a limit of integration, that says I have a specific pressure in mind. So this can't be that same P. So to distinguish what I'm integrating over from the limits, I'm going to just put a little dash here, all right? So this is a general pressure, right, that's changing from 0 to P. This is one limit, this is the other limit, okay? All right. So this gets us a way to determine a fugacity coefficient, okay? All right, the other thing that we can see is that we can determine fugacity coefficients in terms of reduced variables, right? So we're still going to do an integral, but the integral now will be to our reduced pressure that we're interested in, okay? All right, and then it will be z minus 1 over the reduced pressure, again this is our variable, and then dp reduced, okay? So it's exactly the same relationship, but now we're just using reduced pressures, okay? Right, and the fact that we can do reduced pressures, we should expect that, right? Because we know that all fluids behave the same as long as they're in the same conditions relative to the critical point. So this is just an application of the law of corresponding states. All right, so hopefully your ears are perking up at some of the things we're talking about, right? We are necessarily reviewing stuff from earlier in the semester, and that should help us thinking about the final, right? Okay, so we've been doing a lot of derivation, so I wanted to take a moment to just show how we can use the information that we've provided. So what we've got here are two graphs. These are tables. We see that they are both the fugacity coefficient as a function of the reduced pressure. All right? So this pretty much says for any gas, the pressure that you're interested in, temperature you're interested in, you can get the fugacity coefficient from here as long as you know the critical points. Okay? So the example that we're going to look at is what's the fugacity of NH3 at a pressure of 3310 bar, right? And then the temperature is 2025. So we need to figure out which temperature we're going to choose, right? So that means we need to know what the reduced temperature is. That's going to be 2025 K over the critical temperature, which is 405 K, and that comes out to be 5, all right? So that tells us, whoops, that we're going to choose that curve, right? Because that corresponds to a reduced temperature of 5. Okay? And then to find the fugacity coefficient itself, we need to know what our reduced pressure is, right? So that means the pressure that we're interested in, 3310 bar, divided by the critical pressure, which is 111 bar, and that comes out to be 30. Okay? All right, so at this point, what I can do is I can say, all right, there's 30. Come up there, hit that curve, roll over there, and that looks like that's on the order of 1.7. Okay? So we've determined the fugacity coefficient. Pretty clear that it's not equal to 1. It's significant deviation from 1. So that means we expect significant deviation from ideal behavior. And at this point, we can say the fugacity is 1.7 times the pressure, 3310 bar, and that I think is 5360 or 5630. Okay? All right, so we're able to calculate the fugacity, and then the next thing that we want to do is apply this a little bit. So, I have a fugacity. What does it do for me? All right? So basically what we're saying is that we're interested in knowing the Gibbs energy at 2025 K and a pressure of 3310 bar. All right? And we're basically saying that that's going to be given by, I'm going to choose to do this per mole, the molar Gibbs energy at that temperature, 2025 K, and at a pressure of 1 bar plus RT, where that T we know is 2025, ln, now we put in the fugacity, 5630 bar. And we reference it to our standard state, which is 1 bar. Okay? And this basically says I can calculate the Gibbs energy for a non-ideal gas using the fugacity. If we think back, if this was an ideal gas, that we expect ideal gas behavior, I would not have 5630 in there, I would have 3310. And that would be a significantly different value. Okay? All right, so that's an important application of fugacity. And the homework that's due on Friday will give you a little bit more stuff to play with there. Okay? All right, so chapter 9 is phase equilibria. A lot of the things that we talk about, you're going to see are review. We will introduce a few new things. The other thing that's nice about this chapter is it's relatively short. All right? So, in discussing phase equilibria, we're going to be talking about phase diagrams. So just a reminder, phase diagrams, you can get boiling points, melting points, sublimation temperatures. And if you have a phase diagram and I say, what phase is that substance in at this temperature and pressure, you can determine that. Okay? All right. So a big thing that's important on these phase diagrams are phase boundaries. Right? And I just want to emphasize what that means. We have phases in equilibria. That means that if we're on those boundaries, we have coexistence of the two phases. All right? And the other thing that we've established previously, just earlier today, is that on those phase boundaries, the Gibbs energy for the phases, so phase 1 is related to phase, please write, phase 2 by inequality, or delta G of the phase transition is equal to 0. Okay? All right. And then we've also pointed out that if we want to know what the most stable form of the substance is at any temperature and pressure, we know that that's going to occur when the Gibbs energy is minimized. That's what we showed when we looked at the Gibbs energy as a function of temperature. Okay? All right, and this is consistent with us saying that a spontaneous process has a negative delta G. That's another way of saying that Gibbs move to, or that systems move to minimize the Gibbs energy. Right? So there is something new in this chapter, and this is a challenging concept. Right? So that's a word of warning at the outset. It's something called chemical potential. Who has heard of chemical potential before? A number of you? Is my assessment that it's a confusing concept true in your mind? A little bit? Yeah? All right. Okay, so the other thing I want to do at the outset is give the other name for chemical potential. We'll see why it's called potential, but I want to give the other name. And it's basically the partial molar Gibbs energy. Right? And I like this name better because it gives you a little bit more information. This is how the Gibbs energy changes due to the changing numbers of moles of a substance. Right? So it tells us how the Gibbs energy changes by changing the number of moles of particles. All right? So we use the symbol mu to symbolize the chemical potential, which is incredibly unfortunate because I think we've used it like 3 other times for 3 other things, right? But I don't dictate the rules, right? So given this definition, that chemical potential is going to be the change in the Gibbs energy due to a change in the number of moles, holding the other variables constant, okay? All right, so if you think about it, up to this point in this course, we've been talking about impact of changing temperature and pressure. We've been talking about always holding the number of moles constant. Now we're freeing that up and we're saying, how are things going to go if I change the number of moles? And if you think about it from a chemical reaction point of view, this is of critical importance, right? Because if I go from reactants to products, I'm changing the number of moles of reactants, and I'm changing number of moles of product, right? And you've previously heard about equilibria, equilibrium constant. That's going to occur where you've minimized the chemical potential for the system, okay? All right, and then this explanation, and we'll see that this is how it works. The reason it's called potential is that we expect things to go from high potential to low potential, and that's what will be true when we explore chemical potential a little further. All right, so I wanted to take a moment to just review some things about phase diagrams. All right, so we're going to look at a phase diagram. These are both of the same substance. The difference between the two is on the left side, I've got linear pressure scale. On the right side, I have a log scale. All right, so whenever this is the log of pressure 5, that means 10 to the 5th torr. All right, so basically, we have a whole lot more information in this graph than we do in this graph. Okay, but the things that we can glean from these will hold true. All right, so we're going to start by looking at line FE. All right, so for line FE, that's a coexistence curve. And what phases coexist on that curve? So solid and liquid. And I'm going to say that that means they're at equilibrium, right? And so what we can conclude is that every point on this curve, Gibbs energy of the solid is exactly the same as the Gibbs energy of the liquid. Okay? The other thing that we can get out of this is, this gives me, if I look at different pressures, the melting points, right? So this gives me T fusion as a function of pressure. right? I also could look at pressure as a function of temperature as well, but we're more commonly interested in the impact on the melting point. Okay? All right, so moving on to line, whoops, before we do that, let's say that's line FE. Next one up, we'll go to FD. So line FD. See, we change pages here. All right, so line FD, who coexists? That's the gas. All right, and I'm going to put slash vapor. We use those interchangeably, so don't be confused about that. And liquid equilibria. Okay? All right, and then in this case, we're going to be talking about the vaporization temperature or the boiling point as a function of pressure. Okay? And again, because this is coexistence, we can say that G for the liquid is equal to G of the vapor phase. All right? And this concept is going to be pretty important down the road when we start talking about solutions. All right, and then the last portion that we need to think about is, we'll use yellow for that, FC, FC, or CF, whichever way you want to look at it. All right, and then in this case, coexistence will be the solid and the gas phase. So along that curve, the Gibbs energy of the solid is equal to the Gibbs energy of the gas or the vapor. Right? And what kind of temperatures do we get as a function of pressure? What do we call that phase transition? That's sublimation. Okay? All right, so on this relatively simple diagram, we have lots of information. Okay? The only other thing I just want to point out at the outset here is that we see that our melting points depend on pressure, our boiling points or vapor temperatures depend on pressure, but who's got a stronger dependence on pressure? Oh, actually, yeah, I'll agree with you there. But we're more going to be worried about fusion and boiling. It's going to be the temperature of vaporization and boiling. Stronger pressure dependence. And I'll just put in parentheses the melting point because that's what we're comparing it with. Okay? All right, so the other thing's just some generic things to indicate. If I said to you, what phase is this in, you'd have to ask me the question, what do you need to know? What's the temp? You need to know the temperature and the pressure. You have the phase diagram. So that means you have 2 degrees of freedom, T and P. Now, if I tell you that I'm at equilibrium between the vapor and the solid, what additional information do you need? That means we know that I'm lying on this curve. So what do I need to know? Temperature or pressure, right? I only need one. So there's 1 degree of freedom. 1 of T and P are needed. Now, if I told you that I had solid, liquid, and vapor all present at equilibrium, that's the triple point, how many degrees of freedom are there? There's 0, right? There's nothing. It's a one defined thing. The critical point is the same, critical. Okay? All right, so very quickly, some definitions. Normal boiling point, standard boiling point. So normal boiling point means it's a boiling point when the pressure is 1 atmosphere. What is a standard boiling point? It's reference to a particular external pressure Well, what's our standard state when we've been talking about gases? 1 bar. All right? Okay, and then the only other thing I wanted to talk a little bit about is liquids boil when I do certain things to it, right? So let's say I had a container that had liquid in it, and I had left it equilibrate. So that means the liquid and vapor are at equilibrium, right? What can I do to induce boiling in that? I can lower the pressure, right? And so basically what that says is that things boil when P external is less than or equal to the equilibrium vapor pressure. Okay? All right, and we're going to conclude on this picture. These I consider sort of like mini phase diagrams. I've got pressure versus temperature, temperature and pressure. So it's the same information that we've previously introduced. We've just reversed the axes. Pretty straightforward. You can determine the freezing point as a function of pressure and the boiling point as a function of pressure. And I see that you could have waited a little bit longer. It's 2 o'clock now, all right? That disrupted all of us. So apologize to everybody, except for those of you that disrupted everybody, all right? So get out of here. We'll see you guys on Friday, all right? If you did not put your name on the piece of paper or the pad of paper going around the class, please do so. Thanks. Anybody else?